All right. At this point, you should have read the Big Bang reading guide. Um, so basically, what that is it's end notes from a book by Simon Singh about just basically the history of all astronomy. It'd be a great book to have. Like, oh, I could probably almost have an entire class based on it because it really goes from very early astronomy times up through kind of modern day and shows the progress of that. Um, for this video, I just want to focus on uh, the bit about how the Big Bang theory evolved and what evidence that was on, just to kind of clear up some of the later kind of parts of that. Just because I know from past experience, these are some concepts that students don't quite catch, and I feel that they're important. Um, so the first thing is uh, the first great debate that was mentioned in the video, or sorry, on the notes, was a debate between astronomers about these things that were in, real early telescopes just kind of would appear as kind of smudges of white, and they were called nebula. There's something new. And the debate was whether or not these things were the same thing or two different things. In very low power telescopes, they don't look very different. These images are taken, I think, with the Hubble telescope, and so you get much better pictures. And so the debate was, were these two different things or they are the same thing? What they astronomers found out, and I believe this was that they actually located there were some stars in the nebula, and with methods of measuring stellar distances, they found out that some of these nebula were way too far away to be part of our own galaxy. And so they were galaxies unto themselves and very distant. So now that we have better telescopes, we can see that there's a big difference between how something like this, which is what we still call nebula, look compared to something like this, which is what we call galaxies. So the first big kind of debate in modern astronomy, and this is kind of like around the 1900s, the kind of the turn of that century from the 19th to 20th century, was whether or not there were these two different types of things, nebula or nebula, and then galaxies, or whether or not they're all just nebula. And so these nebula are basically just big, huge uh, clumps of gas, and they're the birthplace of new stars. And so the gas collapses under gravity, and once the pressure and temperature of that collapsing gases builds big enough, the star is born. And I think there are some also, there's different types of nebula too that can be formed from uh, explosion of stars as well. But neither one of these are those types of nebula. And then the other type that some astronomers thought were the same thing, nebula, turned out to be galaxies, and galaxies are groupings of billions of stars. Okay, and so there's a couple famous ones like the Sombrero Galaxy. I like just because in a low power telescope it actually does kind of look like a sombrero. Doesn't quite look like that here with higher resolution, but with a lower power telescope it does. And then there's the Andromeda Galaxy, and the Andromeda Galaxy is actually the closest large galaxy to the Milky Way, and it's actually one of the few galaxies that's coming towards us. So sometime in the very distant future, the Andromeda Galaxy and the Milky Way galaxy will collide, and that will kind of, really alter the shapes of the galaxies, and kind of rip them apart, reform new clusters of stars and things. So the Andromeda Galaxy is one that can be seen with a low power telescope. Sombrero Galaxy, I believe, can as well. Okay. Of course, there's our galaxy, which if you go is a galaxy that you can see with your naked eye. You have to go where it's very dark to be able to see it very well. But it's called the Milky Way because it makes this milky path through the sky. So you have to have a very dark sky to be able to see it. This image would be kind of like an artist's rendition of what our galaxy looks like. Kind of a scientifically informed rendition of it. Has to do with where scientists have measured stars to be, like what their distances are and everything else. As far as where we are in the galaxy, so kind of like where my cursor is, that's where the sun would be. So we're not real close to the center and we're not too far out, which is actually good. You don't want to, life wouldn't form or be very well off really close to the center of the galaxy because there's just too much happening there. There's too many gamma rays from the black hole to the center of the galaxy and things like that that would kill off life. Stars at the edge of galaxies aren't thought to be very good places for life because there's not a lot. A lot of the stars out there are kind of newer, I believe it is, and so they don't have a lot of elements present that are needed to make complex life. So not enough, elements like carbon and iron and things like that our body needs. Okay, especially the carbon. Some other kind of things is we don't ever see these in the northern hemisphere, but in the southern hemisphere, there's actually galaxies or even closer, some kind of like mini dwarf galaxies that actually are satellite galaxies and go around the Milky Way. And these are called the Magellanic Clouds. But where they are in reference to us, you can only see them in the southern hemisphere of the Earth. So if you ever traveled anywhere in the southern hemisphere of the Earth, you could look up for these and see these Magellanic Clouds. Okay, so one of the questions is, all these things are so far away. How do we know any of these things? How do we know how big the universe is, how old the universe is? How do we know that these nebula and these galaxies are two different things, and one of them is very much further away, which means it must be much bigger if we can still see it at the same brightness. Okay, and so one of the ways we know about stars that are out there and like the different types of stars. So even to like not to the naked eye so much, but with a pair of binoculars or a low power telescope, if you look around the night sky, you will find that there are stars that are different colors. And so, different color stars, you can have really hot, bright stars, so blue giants. You can have really bright red stars, which are the red giants. Okay, so those are ones that you can see almost with the naked eye, but it's usually hard to see if they actually have color without actually using a telescope or binoculars to just gather some more light in. But then we can get more specific by looking at their spectrums, and we can see like what elements are present in these stars, and we can classify them based on like the types of elements that are found in those. Okay, the most common spectrum that astronomers are going to see in stars are hydrogen. So hopefully by doing the reading, you see that most of the universe is hydrogen, like 99 point something percent of the universe is made up of hydrogen, with another 0.8% being helium, and all the other elements make up as the universe is a total, like a very small portion. So this is hydrogen spectrum. This is the absorption spectrum. So like the sun would put off like all colors of light just because it's hot, and then the hydrogen that's like in between the sun and us absorbs colors of light, and those leave distinct dark bands. Or what you're going to be doing in lab, if you heat up just a sample of hydrogen itself, it will emit those same colored bands. Okay, so those are that's one way we can identify like what elements are out there in stars. So we can kind of get the types of stars, and knowing the different types and what elements are present can help astronomers and physicists figure out what kind of mechanisms would cause that to happen. One of the ways we know how far away stars are, and this only works for very nearby stars, and near is a very relative term, is using the whole concept of stellar parallax. So between the summer and the winter, the Earth, of course, moves around the sun. And if we're looking at a nearby star, where it appears against the faraway background stars in the winter and where it appears in the summer is very different. And so that concept of things appearing in different places based on your perspective is called parallax. And the farther away something is, the smaller the parallax gets. And so you can actually, by determining how much parallax there is, you can figure out how far away things are if you're able to measure it. You use parallax every day of your life if you have good depth perception. And to see this, you can hold your finger up in front of your face, close one eye, look at what your finger's lined up with, and then switch which eye is closed and which eye is open, and you will see that your finger moves against the background. Your brain is always comparing these two different images from your two different eyes to be able to judge how close things are by looking at like where does an object appear in one view versus where does it appear in the other view. And this is actually how 3D movies work. The glasses you wear make it so that your two eyes are actually seeing two different images on the screen. Where if you take them off, the movie screen is going to look blurry because those two images are superimposed on each other, and you need the 3D glasses to separate that out. Okay, so that's stellar parallax and how we tell distances, but that only works, like I said, for the very nearest stars. The other way to identify how far stars are is using the method of standard candles. And so you guys are going to be doing a lab this week, and actually kind of already did lab, so we're just going to be revisiting it, where you'll look at how stars get dimmer and dimmer. Any light source will appear dimmer and dimmer the further away it is. And so if we know how bright a star is supposed to be, then we can figure out how far away it is, and by how bright it appears. And the question is, well, how do you know how bright the star is supposed to be? And there were actually studies done with these Cepheid variable stars, and that's one of the things you read about, that those were the first like rulers to the universe. Is that Cepheid variable stars we found from ones that were close enough to use parallax had a very good relationship between their period of variations, because they get brighter and dimmer and brighter and dimmer, and how bright they actually are. And so if you can measure a variable star's period of variation, and you can measure how bright it appears to be, and you know then from its variation how bright it's supposed to be, then you can figure out how far away that Cepheid variable star is. So that really helps calibrate things. And there's other standard candles like supernova, like have a very specific brightness because they have a very specific mechanism that creates them. So scientists can tell by the duration of a supernova how bright it is, and so then they can figure out how far away it is based on how bright it appears. One thing that's really important to the Big Bang model is this cosmic microwave background radiation. And so this is basically was predicted by the Big Bang model and actually measured years later after it was predicted. And that's how you know you have a good theory, that it's able to make predictions. Not that it just fits data that we already see, but that it can predict new observations, and then people can go out and look for them. So the cosmic microwave background radiation is just basically radio waves that are coming from all over the universe. And this is because of when the universe was still very small and very hot, it was opaque to light. Light couldn't travel through it because every bit of matter in the universe was charged, and light can't travel through charged objects. It just bounces around. And then once the universe cooled enough to where the electrons and protons got together to make these hydrogen atoms, then light all of a sudden became transparent, and light was released and just sent every which way throughout the universe, and that light's still traveling to this day. And then because of the expansion of the universe, even though this light would have started off as very short wavelength, very high energy light, the expansion has elongated the wavelengths. The energy of the light has gone way down as it's spread out over a larger area, and so now it's microwaves or radio waves. Okay, and scientists are still trying to make more and more detailed measurements of this cosmic microwave background radiation, because the trying to understand like the differences between like where the universe was hotter and where it's cooler helps try to understand like how early galaxies could have formed. Looking for evidence of gravity waves that would lead us to better understanding of how gravity works and all these things. So the cosmic microwave background radiation is something that's still being studied very intensely. Okay, so just in terms of what the story of the Big Bang says, basically the universe started off all condensed, at a very super dense state, and expanded outwards from there. Okay, so first, we had atoms not being able to stick together, and then as it cooled, they stuck together, and then you form like early galaxies, and then the galaxies matured, and then finally you could make planets and things. Okay, so lots of these. I don't know. It shouldn't just show one. Obviously, there's billions and billions of planetary systems. Okay, and then just the steady state theory was the competing theory of the Big Bang, and basically it said that the universe does expand, but new matter is always being created that fills in the gaps. And I'm out of time, so I guess I can't go into that too much, but you can read about it here.